Let's take a little break and just talk about some applications related to systems of linear equations. Now, in the textbook, you can see some examples of this in Chapter 1. There's actually a couple chapters devoted to applications, and some of the places you'll see applications are situations like in chemistry where you're balancing chemical equations, chemical processes. There are examples in electrical engineering if you're doing circuit analysis, Kirchhoff's loop laws and things like that. Some of you maybe have even done some of these things already. Also in Calculus 2, if you remember partial fraction decomposition, a lot of times that involved solving a system of linear equations. I want to focus here at a couple of different applications. The first one I want to look at is curve fitting and polynomial interpolation. And I start off with an actual theorem, and this is if we have n points in the xy plane with distinct x coordinates, there's a unique polynomial of degree n-1 or less whose graph passes through those points. And the polynomial is something we call an interpolating polynomial. So for example, if I have 3 points with distinct x coordinates, if I'm graphing an xy plane, that means moving left to right. I'm not going to have one point above another point, right? Above or below in the same vertical line. So this has one x coordinate, some y coordinate. This one is another x coordinate, and then suppose we have this point here. Now there's 3 points here, so by this theorem, if n is 3, then 3 minus 1 is 2. There's a unique polynomial of degree 2 or less whose graph passes through these points. And we can imagine what it might look like. If it's degree 2, we know then it must be what? Some sort of parabola, and obviously opening downward. Degree 2 polynomial would look like that. Now it says degree n-1 or less. Well, if n is 3, in our case, 2 or less would be 2 or 1. How can you have a degree 1 equation? Well, if on the other hand we have 3 points with different x coordinates that look something like this, you can see that instead of a quadratic or degree 2 polynomial fitting through them, we would, if they're fall in a line, then we have a linear function, right, that passes through those 3. And so that's sort of the idea behind this theorem. So here's the general approach to this. Suppose we have n different points, and I've denoted these points with subscripts. So there's our first point, our second point, and our nth point. These would be points that we have that are given. And of course the x coordinates x1, x2 to xn are all going to be different. And we want to find this degree n-1 interpolating polynomial. So what would that look like? Here is a degree n-1 polynomial. I've put this in not decreasing but increasing order. A lot of times we'll do that. A lot of times you're used to writing polynomials from the highest degree term down to the smallest degree term. But here we start with the constant term. So the a sub 0 here is the constant term. A sub 1 is the coefficient of the x term. A sub 2 is the coefficient of the x squared term. And a sub n-1 is the coefficient of the x to the n-1 term. So these a's are what we're looking for. These are the coefficients of our polynomial. That's what I want to know. And so it's important to know that in this process, the a's are the unknowns. The x1 and y1s, x2, y2, and so on, these are given points. They are going to be our known values. So what we do is we plug in our n points into this polynomial. So I replace x with x1 and y with y1, and I get this equation. Okay, kind of swap the sides of the equation above. If I replace x with x2 and y with y2, I get this second equation, and so on all the way down to plugging in x sub n and y sub n to get this last equation. And what do we have here? Remember, the x1s and the y1s are all be known values. So we will have a system of n equations in the n unknowns. Why do I say n? Because I know there's n-1 here, but remember we start at a sub 0. So going from a sub 0 to n-1, there are n variables. So the a's are the variables. And so from this system, we can write the augmented matrix. Notice the augmented matrix consists of the coefficients of the a sub-zeros in the first column, notice they all have a coefficient of 1. Right? In the second, and be careful, a sub 1 is the unknown in this case. The coefficient is x sub 1. Right? The coefficient here is x sub 2, and so on. Right? Here the coefficient is x sub 1 squared, and so on. Right? And you see this pattern develop. Right? And so we can find our interpolating a polynomial. In particular, we can find the values of a sub 0 through a sub n minus 1, the coefficients, by solving the system, doing Gaussian elimination. In this process, it would be okay to use your calculator to put it immediately in reduced row echelon form and get your result in these applications, and that's what we're going to do. Okay, so here's the theory. Let's see it in practice. Here's a specific example. Find a quadratic polynomial, quadratic degree 2, that passes through these 3 points, right? And so here we have 3 points. We're guaranteed to have either, of course, a degree 2 or a degree 1. In this particular case, we'll see these points are not falling in a line, and so we're going to have a degree 2 polynomial. Okay, so we just went through all that theory. Do we need to redo that? No. I mean, you don't have to memorize that this augmented matrix form. I mean, you could. But what we'll just do is we want to find our quadratic polynomial. So I'm going to describe that this way. It's going to be constant term a sub 0 plus coefficient of x, a sub 1, plus a sub 2, x squared. Right? So it's a degree 2, it's quadratic. So I'm looking for a sub 0, a sub 1, a sub 2. What are those coefficients? Once I do, then I will have the interpolating polynomial. And I plug in my points. Here's my x1, y1 point. So my point -1 comma 0, right? That's the value of x. That's the value of y. And I'm going to replace x and y with those values. I'm going to do this right side of the equation first. And replacing x with what? -1. Equals y, which in this case is 0. This is my first equation. Let's clean it up a little bit. I'm going to get a sub 0 minus a sub 1, right? And then -1 squared is positive 1 plus a sub 2 equals 0. So that's our first equation in 3 unknowns. Second equation will come from our other point, 1 comma 10. Right? Here x is 1 and y is 10. Well, if x is 1, we just get a sub 0, a sub 1, 1 squared is 1, a sub 2. So I get a sub 0 plus a sub 1 plus a sub 2 equals y, which is 10. There's my second equation. And then 2 comma 5, x is now 2, so when I plug in I get a sub 0, 2 times a sub 1, and then 2 squared, which is 4, times a sub 2. And that equals the y value, which is 5. So this is the system of linear equations that I need to solve. Okay? So how can I solve that? Well, I'm going to get my augmented matrix from this system. And I look at the coefficients of our unknowns. Our unknowns, again, are a sub 0, a sub 1, and a sub 2. So the coefficients in the first equation, 1, -1, 1, and then the constant term is 0. 1, 1, 1, 10, and so on. Okay, so this is our augmented matrix, and I'm going to call this matrix A just to talk about it. And what I'm going to do is I'm going to put this matrix into its reduced row echelon form. So I'm not going to do all the steps in Gaussian elimination. We've been doing that, and you've worked on that process, you know, how to do that by using those 3 elementary row operations. We're going to use the calculator's command. I'm going to use the calculator's RREF command. And I'm also going to convert that to fractions. Okay, it turns out we get some fractions, and that's what we want to do. So let's just go ahead and do that right now. I'm going to get into my edit in matrix. I'm going to edit matrix A, and it's going to be what size? 3 by 4. And I'm going to enter in the coefficients and constant terms in here. Okay, and as always, double check very carefully that we've entered in the columns correctly, 1, 1, 4, negative 1, 1, 2, and 1, 1, 1. So I want to make sure that's in there correctly. And then I'm going to quit, and I'm going to go back into matrix, over to math, and I want to go all the way down to where I see RREF. Second matrix, number 1 is matrix A. Copy that there. Close the parentheses, and then under the math button, right, remember that's where that convert to fractions is. That will help us out immensely. We do that, and there is our reduced echelon form. Okay. And you see these fractions that we have, and that's what we want. That's why we want. You don't want to have this to be negative. You don't want to write this as negative 3.33. That's an approximation. You want the exact value. So notice that we have then these are the coefficients of what? A sub 0, right? A sub 1, A sub 2. So A sub 0 is 25 thirds. A sub 1 is 5. And A sub 2 is negative 10 thirds. Okay. But again, what's the answer then? The answer we're looking for is the interpolating polynomial, this quadratic polynomial. So my answer then is, from these results here, y is a sub 0, which is 25 thirds, plus a sub 1, which is 5, times x, and then plus a sub 2, which is negative 10 thirds, so plus a negative or minus 10 thirds x squared. That is your actual interpolating polynomial. Now, could we make a mistake somewhere in here? Sure. But we should check and make sure. We've said that this passes through these points. Does it indeed pass through these points? Well, you can graph this polynomial now and plot these points and confirm that. And I've done that down here. Here's a graph of this polynomial, interpolating polynomial will come up with. Does it pass through the points? Our points were negative 1 comma 0. That's right there. 1 comma 10. That's right there. And 2 comma 5. That's right. And so there it is. We have fit the curve through those points. And the neat thing is, you can, have many points, right? I mean, if you have 10 points with different x coordinates, then you're guaranteed to have a degree 9 or less polynomial that will fit through those points. Okay. So interpolating polynomials. That is one application. The next section we'll talk about network analysis as another application.